Hello everyone, welcome back to our Polynomial Functors course. This is day 10, and today we're going to be talking about products in the category cat-sharp, which is our name for the category of categories and cofunctors. Now, one thing I should say is, why are we even talking about this? This is a very sort of specific phenomenon that happens in this category, and why are we spending an entire class on this? And I think it's a good sort of case study for, first of all, appreciating how cofunctors are very different from functors, right? Like, the behavior is very different. And in some ways, our cofunctors, why we like using cofunctors, they kind of capture this slightly more generalized idea of a dynamical system, of these polynomial morphisms as dynamical systems. And I'll be talking about how you can think about a cofunctor as a sort of like a kind of like very specific type of dynamical system where you can compose inputs, essentially. And so this sort of kind of playground we're going to be messing around in will help develop hopefully some better understanding of what these cofunctors are and like how they work. And of course, specifically, what products are going to tell us is how to think about sort of cofunctors into two different categories as a cofunctor into a single category, because that's what the universal property of a product is. And we'll be thinking about like what exactly that means. And it's going to turn out to be a little bit, it's going to turn out, like the math is going to turn out a little messy. But I want to always sort of like bring us back to this sort of intuition of cofunctors as these dynamical systems. So we'll see how this goes. Before I get into it, though, I wanted to review our cofree comonoid construction. So given any polynomial p, we can get the cofree comonoid on p. And cofree comonoids are just categories. And so specifically, what kind of category is this? Well, I like to think of it as the category of p trees, where the objects are what we call these p trees. So these are trees built up of the corollas from p. So for example, if let's say p were y squared plus 2y plus 1, and you might remember this example from I think day 2 when I was explaining this a little more. I think I was a little more rushed when I was explaining this, but hopefully you can come to appreciate this better now. Well, you can think of this p as having 4 different corollas, one with 2 directions, 2 with 1 direction each, where I've sort of drawn them in like different directions to kind of distinguish them, and this one with no directions. And these p trees are just trees that you can build out of gluing all these together. So for example, we could always start with something like this on the bottom. Here, maybe we're going to glue this here only to the left. Maybe we only glue something to the right. Maybe we glue 2 things here. But maybe we glue something with no directions here. Now, one thing to be careful of is that if we don't glue the thing with no directions, we have to keep going, right? Like we have to give every direction some position that we've drawn. So maybe this just goes on forever this way. And let me just draw something here. I'm going to stop it there, and let's just, I don't know, stop it there. OK. And so this is maybe one of the objects in our category. And the objects in our category are going to be generic trees like this. And the morphisms in our category, you can think of them as rooted paths along this tree. You can equivalently think of these as vertices of this tree, because that's just where the path ends. But I like to think of the morphisms as maybe like a path. So maybe pick this path that goes here, here, and here. And notice that this is just picking a series of directions, right? Picking a direction, and then at the position there, picking another direction, and so on. And then maybe stopping at some point. You can stop whenever you want. And well, so that tells us the morphisms out of each object. And that's a very sort of poly-oriented way of talking about categories. I tell you what the objects are, and I tell you what the morphisms out of each object are. And now I have to tell you not just what the identities are and what the composition rule is, I also have to tell you what the codomains are, because I haven't specified that yet. But here, I'm just going to say the codomain is this tree, this new tree that you reach, this subtree, rooted at wherever the path ends. And that's another P tree, so that's another object in our category, and so that can just be our codomain. Okay, and well, what's the identity? It should be a morphism that takes us from this tree to the same tree. Well, there's always something that does that. It's just this, this rooted path that doesn't go anywhere. It's just like, it just stays at the root. And so this and the subtree rooted here is the entire tree, so you can see clearly that this is just a morphism from this tree to itself. And then the way these morphisms compose, well, if we start with a path here, and then we end up at this subtree, well, this subtree, the morphisms coming out of this subtree is just some other path, and you'll use another color, some other path coming out of here, maybe it ends there. Well, you can see that to compose these two paths, you just glue them together, and you get one long path coming out of this original tree. And its codomain is, in fact, this newer subtree up here. And this is our category. Yeah. And yeah, there's this kind of, I don't know, there's this interesting, it feels almost like a topological structure on this. And in fact, we did say that, let's see, co-free sheaves on this category are precisely our dynamical systems with interface P. And so you can form, I think David mentioned last time, we can form a topos of these, and that has a certain internal logic. We won't go into detail about that, but you can sort of see kind of geometrically maybe what's happening here. Okay. Another way to think about these, though, is this, right, this idea that we have a, sorry, what was I saying? Yes, okay, so for any, this is the cofree construction, so we have this adjunction from, that relates, maps in poly from an arbitrary category to a, or the underlying polynomial of an arbitrary category to a polynomial P, and cofunctors from that category to this cofree of P. And well, specifically, we can, we're very interested in this particular category sy to the s, where morphisms in poly from sy to the s to P are just dynamical systems with interface P and state system S. And I talked about sort of the whole reason we were doing these comonoids in the first place. When I introduced these comonoids, I talked about the idea that this morphism really only tells us one step of this dynamical system. It tells us if you have a state here, what output it's going to give you here, and then if you pick an input here, which state are you going to end up back over here, or which sort of thing here. But it doesn't sort of keep cycling through. You have to kind of manually think about, okay, this element matches up with this element, so I can keep going. And if you actually wanted to formally cycle through this, you would need to make use of the the comonoid structure on sy to the s to obtain these more general maps, sy to the s to some p, to some p composed with itself n times, which, if you'll recall, is obtained by sort of this map that comes with this comonoid. And then here, this is just this map tensored with itself, or composition tensored with itself n times. And so that tells you how to operate sort of n steps of this. For each state, it tells you not just the output, but for every possible input from there, what output you would get there. And then for every possible input there, what output you get there. And all of this sort of n times. And it tells you sort of all the, I guess, sort of n effects of like length n. But actually, we can, what this adjunction gives us is a way of reading this as a cofunctor, which tells us how to not just cycle through this once, not just cycle through this n times, but just one kind of morphism that tells us how to cycle through it any number of times, right? Because if we take an object, what it sends each sort of element in S to, what each state to, is an entire P tree. It tells you what output you get, but it also tells you for all the inputs what outputs you get for each input, and then again for each layer there, and again, and it's going to keep going and eventually give you a tree that looks like this, one of our P trees. And that tells you everything, basically everything you need to about this system. It tells you the entire sort of destiny, basically, of this one state. And then following one morphism along here, following a series of inputs you could give to this, it's going to bring you back over here and tell you which morphism you're going to sort of like that's going to end up at, and then that morphism tells you which state you're going to get to. Yeah, and so that's one way, another perspective to look at these cofree comonoids. So any questions there before we move on? Yeah, and so we can think of these cofunctors, sort of general cofunctors from maybe like some category C to some category D, as maybe some sort of generalization of this. There's a couple ways you can think about this, but one way is that, well, if we have, right, so we have some state, right, like this category C, its objects sort of tell us our states. That's going to send it to some other sort of like sort of generalized output in D, right? And this is going to carry some sort of information about this state. It's going to be the output of the state, and then whatever input we give here, whatever sort of morphism out of the object in D we give here, maybe it's going to go to some object here. That's going to give us, or if we pull this morphism back through this cofunctor, it's going to give us some other morphism back here. So it's this delegation that we've seen quite a few times, right? It tells you, okay, I'm in this state here, and you see this. I'm in this state. I tell you this. You can make a choice. You can make a choice based on any sort of morphism coming out of this output. That's your input. That's the input you give me, and then that's going to give me something out of my state. Now, the fact that it's a cofunctor, though, tells us something extra, which is that it's going to end up at a certain state on my end. And actually, the state that it ends up on at my end is exactly the state that's going to map to, or is going to be a state that's going to map to whatever state you ended up here on your category. And so we have these sort of like composable delegations, right? Now I'm here, and now you can give me another morphism over here. You can tell me another thing to do. That's going to give me something to do over here, and then I'm going to end up in a spot that I can then pass back to you. You tell me something again, pass it back to me. Or you could just tell me exactly how to get over here by composing these two morphisms, which is something we can do in a category, and that tells me directly what I can do over here. And so there's this sort of generalized composable delegation of these decisions. And that's kind of the language or the way we're going to be thinking about these products here. Because, well, what is let's see, okay, I just said that that's how we're going to think about these products, but before we get to, what do I want to do? Yes, sorry, I was going to mention one other thing about these cofree comonoids. One thing to highlight, which we'll use, is that when P is a monomial, for example, in the form by to the a, I guess that's the only example. Well, let's think about what the cofree comonoid on this monomial is. Well, it's going to be what I'm going to call these, like, they're these like by to the a trees. I guess I'm going to sort of abuse this notation here. I'm actually going to call these objects sort of b-labeled a trees. What do I mean by this? Well, let's say a was, I don't know, let's say a was 2 and b was 3, right? So these 3 labeled 2 trees. Well, a 2 tree, what I mean by a 2 tree is just a binary tree. So it's going to be a tree where everything, and it's an infinite binary tree, where everything just has 2 children, and it's just going to keep going up this way. And then we're going to label each node with a 1, 2, or 3. So with any element of this B. So maybe this is 1, 3, 1, 2, 3, 2, 1, and so on. And yeah, and you can see that this is exactly sort of what we get if we follow this definition. And then a morphism in this is actually just going to be, well, you just keep picking elements of A, right? Like you say, oh, here we're going to go left, here we're going to go right, and then maybe we stop there. And when you think about that, all the morphisms here are just lists of elements in A, right? So literally the set of morphisms here from out of any object is just what I'm going to denote as list A. So you might have also seen this as A clean star. This is just the sort of set of all finite sequences of elements in A, or the free monoid on A. Yeah. And so, okay, so what is this actually as a polynomial? Or what's the polynomial that carries this cofree comonoid? It is going to have, it's going to be a monomial itself because all of its morphisms are just going to be elements of list A. But its objects are going to be like these B labelings of these because we know sort of which element of B each of these outputs. So it's going to look something like that. Yeah. One cool example of this, like why this is interesting, I think the reason why this is interesting, we talked about, I think in one of our discrete, when we were talking about these examples of dynamical systems, we talked about how you can think of a deterministic automaton, deterministic state machine, as a morphism from sy to the s to 2y to the a, where a is maybe like the alphabet of our state machine, and these elements of 2 tell us whether we accept or whether we're in an accept state or a reject state. So this is just each state tells us whether we accept or reject it, and then from each element of our alphabet, from each letter in our alphabet, that takes us to another state. And so that's our deterministic automaton. Maybe we don't have it, we don't tell you what the start state is yet. But if we pass this through our adjunction, we actually see that this is precisely a cofunctor from sy to the s to the cofree comonoid on 2y to the a, which if we plug in here is just 2 list A, y, list A. And so I want to highlight this on objects function of this cofunctor here. It sends each state s, each starting state s, to an element of 2 to the list A, which is exactly a subset of lists on A. Lists on A you can also think of as words you can make out of the alphabet A. So this actually tells us exactly if we give a start state, this set is exactly the subset of the words that we accept by this automaton. And so I think that's a sort of neat sort of in action kind of example of this. Okay, that was a bit of a diversion. Let's get back to talking about what we're going to talk about today, which is this idea of products. Okay, so what do I mean by a product in cat sharp? Well, it's going to be this thing that tells us if we have a cofunctor into some category C and a cofunctor into some category D. Huh? Sorry, that's an E. I apologize if that's a little. Yeah, there we go. I don't know. Maybe I'll add a thing there. Thanks. Yeah, if we have a cofunctor into C and a cofunctor into D, can we package this information up as a cofunctor into a single product, C times D? And maybe I'll dash this. And the reason I put like a sharp above this times here is because I don't want to confuse this with the actual sort of, well, maybe not actual, but the product of categories we're familiar with. And of course, there should be projections from this category to C and D. OK, well, why am I not wanting to confuse this with the usual products of categories? Well, let's consider an example here and try to see, yeah, let's see if we let C, the product of C and D in cat sharp just be the same as the product of C and D in cat, does that work? Our familiar sort of category, product of categories. OK. Let's take a relatively, or at least seems like it should be a relatively simple example, and take the product of this category where we just have one morphism from here to here. Of course, they also each have identity morphisms with itself. I'm going to draw it like this because the product is really, in cat, the product in cat would be something like this. It's going to have 4 objects and I believe 9 morphisms because 3 times 3 is 9. And yeah, it's going to look something like this. I haven't drawn the identity morphisms, but this composes to this, which is also the composite of this. And so that's what the product is of usual categories. And now we can see that there's kind of a cofunctor. Right, we need some projection here. And you can see that, OK, we just send the objects to sort of where they came from, same as products in cat. And then, well, let's see. If we send this over to here, we should be able to like lift this arrow over here to some arrow here. Well, let's just say we lift it to this one, right? That seems like a pretty standard choice. I guess we could also maybe choose to lift to this one, but it seems like maybe safe to like go with the identity one because we know that that one always exists. OK. Now, OK, so we're going to say, OK, is this the product? Well, let's find some other category that's going to have 2 cofunctors into each of these arrows and see if it matches up with what we want. So I'm going to draw something here. And this is a rather strange-looking category. It's not too weird. And again, it's going to have cofunctors into each of these. And again, I've drawn it suggestively so that you can see where each object projects to. So both of these objects, these are both going to be sent to here, and they're both going to be sent to here, whereas these 2 are both going to be sent here, but they're going to be sent to each of these here. OK. And yeah, there's really only one way we can, or let's see, what am I saying? So this goes here, but there's only an identity morphism out of this, so you don't have to worry about lifting this back here. It just goes to the identity. But this does also go here, so if you look at this and lift it back up over here, we're going to say that it goes to this arrow here. I think that's the only choice you can make. Let's see. Now, if you're here, well, you project to here. There's no non-identity arrows out of here, so that's safe. But if we project to here, there's a non-identity arrow here. That's where we're going to lift up to this arrow. And finally, if we're here, we don't have to worry about this. But here, we have an arrow telling us that we go this way. And so we're going to go this way. And so you can see that this is kind of a weird system where if you have the system and you're only interacting it with this interface, right, this cofunctor into here, we have, or I guess I'm drawing. Let me just. yeah, this cofunctor into here, well, if we start here, we actually can't do anything, right? Like we're already stuck because there's no non-identity arrows out of here. But the fact that there's another interface here actually sort of lets us get unstuck, right? Like this is going to bring us out over here, and then now we actually can operate with this interface, and that's going to bring us here. And so there's sort of this weird thing where like two interfaces like do a lot more than just like each of these interfaces separately, right? And you can get yourself unstuck if you have multiple interfaces acting on the same system. And that's going to be a problem when we try to find what this map is here. So if this were to be our product, there should be a canonical cofunctor from here into here. But we already run into a problem because this is going to need to map to this if it's going to, right? Because this is going to map to each of these two. It's going to have to be mapped to this point over here that maps to those if it's going to commute. The problem is now, if we map this here, see where this arrow lifts to. Well, the only arrow this can lift to is the arrow to here. But here, if we lifted here, it's going to end up here, which these don't match up anymore. They don't project to the right spots anymore. And that's going to be a problem. Yeah. Not only is that going to be a problem, right? Like you might say, okay, maybe we do want this arrow. Maybe we throw in another arrow here, and we say, okay, this lifts to that instead. Okay, that solves this issue. But what about this one? This one, if we go over here, well, we actually do want this. If we lift this over here, we do want it to end up here. So you can see that this shows that we're actually going to need at least two objects here in this product. We need an object that's going to let us map over here when we project it there and then bring this back here. We need a different object that's going to map us over to here. Okay, but then once we mapped over here, well, we also still have like this comes over here, right? By if we lift this arrow up, and so somehow this needs to come over here. But also, this didn't have to come over here, right? I could have easily changed this to like point to itself instead. In which case, this would need to be replaced with yet another object that sort of does this pattern here. I'm sorry, my picture is kind of colliding. You can already see that you need a bunch more objects than just 4 to account for all of the possible like futures of what could happen in this system here with these cofunctor projections. Yeah. So this looks like not just usual products in cat. So let's try to figure out what it actually is. And okay, maybe this arrow sort of like example is already too complicated for us. So let's go even simpler and let's just think about discrete categories. Fortunately, that's actually not going to be too bad because I guess you can just sort of stare at it and think about it. But another kind of formal way to do this is to note that we have this adjunction between cat sharp and set, where for, let's see, I believe, yeah, so for any, I believe this is the right way. Yes, for any category, we can just take its objects, CF1, send it to a set. For any set, we can send it, for any set A, we can send it to the discrete category AY. You can see that, you can tell pretty easily that this is an adjunction, right? Because a mapping on the objects already gives us a cofunctor into the discrete category because you don't have to worry about, like the identity morphisms are already decided, you don't have to worry about any other morphisms. And so, because this is a little bit of a roundabout way of saying it, but because this is a right adjoint, you can see right away that the CY times dy in cat sharp is just c dy, because right adjoints preserve products. I'm going to be using this at least 2 more times. But yeah, so this is a neat example, right? Because if you think about it, a cofunctor into a discrete category just tells you the outputs, right? There's no sort of inputs back. It's just giving you whatever output you get in C, whatever output you get in D. Well, you can just think of that as a pair of outputs, one in C and one in D. So that works as you sort of expect it would. It seems like it's when we introduce arrows, non-identity arrows, that things get a little more hairy. Right, so this was discrete. Now, next example is cofree comonoids. Now, the cofree functor is also a right adjoint, which tells us that the product of 2 cofree comonoids in cat sharp is just the cofree on the original, the products of the original polynomials. Okay, so what does this mean? Let's unpack this, right? So somehow we're thinking about this category of like PQ trees. And so these are going to be, right, and so what are the corollas? What do the corollas in PQ look like? Well, remember, they're going to be a corolla, you take a corolla in P, and you take a corolla in Q, and so that's a pair of positions. That's the positions of PQ. But then we add up we just add up the directions together. So let's say if we have maybe a corolla that looks like this in P, and then a corolla that looks like this in Q, well, that's going to correspond to a corolla that looks like this in PQ. So that's exactly this idea that we are outputting an output for each of these original interfaces, but the inputs we can give in are either an input from one of the interfaces or an input from the other interface. And so you get sort of trees on this. And you can see how, yeah, that's sort of what you would expect the product to be. As a specific example, maybe a slightly more concrete example, if we use these monomials, I'm bouncing around a little on the board here, but if we take the product of the cofree comonoids on 2 monomials, so let's say we have cy, I'm just going to draw parentheses around them because it's like I can sort of factor out this list A times dy list B. What kind of thing is that? Well, it's going to be c dy list A plus B. Remember, we multiply the sort of positions and add up the directions, and that's the new category we're going to get. And so these are going to be trees where each, I'm going to draw it as a little kind of cartoonish, but they're going to be trees where each label is going to be a pair of labels, one from C and one from D. And the arrows coming out of it are going to be both all the elements of A and all of the elements of B. So you should think of this as like a bunch of arrows. These are sort of all the ones from A. These are all the ones from B. And then for each of these, we also have to pick a pair of elements from C and D, and then a bunch of arrows from A, a bunch of arrows from B, and so on. And that gives us a very nice conception of what's going on there. The problem is, in general, right? This is a very nice example because we have cofree comonoids. But in general, the morphisms are a little messy, right? Cofree comonoids have this really nice thing where we can express all of their morphisms as like these pads on a tree. But usually we don't have all our morphisms nicely structured on a tree like this. We might have morphisms, right? We might have we can always draw like a corolla out of any one object, right? But maybe, right, maybe this arrow is the identity morphism. So in the case of like the cofree comonoid, we don't draw that at all. We just think of that as our root. But then maybe like this morphism that we've drawn is actually, you can actually factor it through this morphism that we've drawn, which is never something that happens in our cofree comonoids. And so we're going to have like equations of our morphisms that are going to mess things up a little bit, possibly. Maybe right. Maybe I can draw it like this, right? There's some like codomain here that takes us there, but then that's actually the same as like this morphism there, or something like that. And so, in other words, right, so there's going to be like slightly more complicated composition rules that's going to make products more difficult. So let's think about, instead of just like these cofree comonoids where our sort of possible morphisms are just these free monoids on A, let's just think about what happens when our morphisms are monoids in general. But before we sort of commit all the way, let's just focus on monoids first. Let's just focus on one object categories and see what's happening there. Well, once again, let's see, where are we now? This was, I think we're on number 3. If we have monoids, these are, I think this is a little confusing, because when I say monoids, I mean monoids in set, which are one object categories. And we can think of these in terms of yet another right adjoint from, I think David mentioned, we have a right adjoint from the opposite category of monoids on set. Can you pass me my AirPod case there?
I started recording.
Test it. Thank you. Testing? Testing? Okay, we should be back. Okay.
Is video there?
I think that's the video, right?
Okay. They say they want the whole monoid thing repeated.
Yes, sounds good. Okay, I'm gonna get some water first. Hopefully the audio is back now. Sorry about that. Might also. Okay, yeah, I think we can get through this. Yeah, let me just go over this monoid stuff again. The idea is that we have a, we have a right adjoint from the opposite category of monoids on set into cat sharp, sending each monoid to its one object category, corresponding one object category, which tells us that the product of two monoids in cat sharp is actually their coproduct as a category. The coproducts of monoids are also known as free products, which is a little confusing. They're denoted m star n with a star. And if we think about what kind of elements this monoid should have, well, it needs an identity. It needs an inclusion from M, so it needs all of the elements in M. It needs all of the elements in N, and it also needs formal products of all of these elements, right? Now, if we have just two elements of M, we multiply together. We can multiply them together to get another element of M. But if we have one element from M and another element from N, we don't really already have a product for that, so we just define that formally as another element of this coproduct. And so, in fact, all of the possible elements of this coproduct are just going to be all of these alternating products of elements from M and elements of N. So maybe M1 times N1 times M2, maybe all the way to some M sub k. Of course, you could also start with N, or you could also end with N. And the way we multiply these together is, well, we just sort of put them right next to each other. And if we end up with two elements of M right next to each other, so this isn't alternating anymore, but we can just sort of multiply that together. We can just use the multiplication of M to sort of smush all of these together, and we're going to eventually end up with an alternating product of elements of this monoid. Yeah, any questions about any of that? Hopefully, I rushed through that a little bit. Okay, because this idea is going to come back up again in general. Because our general case of products in cat sharp is a generalization of this when we also have a bunch of different objects, when we don't just have one object. And I'm going to give you two different ways to interpret these. One is nice because it's rather short, but I can tell you exactly what the product should be in category theoretic terms. And in fact, it tells us not just these binary products, but any small product. Let me use this. But I'll just use the example of binary products for now. and I'll briefly mention how to generalize these, we can create what's called the free monoidal category on two comonoids. What do I mean by that? Well, by that I just mean we have a category. It's a monoidal category, so it has some monoidal operation, and it also has two comonoids in it. I'm going to call them maybe little c and actually, what do I want to call it? Yeah, okay, little c and little d. And I'm still just going to use y and the little triangle for this. And what you're going to get, OK, so you have these, it's a category, and it contains these two comonoids, and it has this monoidal operation. And that's all I tell you about the category. And you just see sort of what's the simplest like category you can get out of this. A little informal, but well, you should also be able to get a bunch of morphisms. Right, like from C, just from this comonoid, you can go from C to sort of any number of these C's tensored with each other. Same for D. But we should also get objects of the form, maybe C, tensor D, tensor C, 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 D, C, something like that. And we should get all of the different ways of tensoring C and D together, and all of the morphisms that this should tell us we should have. So for example, out of this, there should be a way of like going, right, we have two D's in a row here, so there should be a way of going from this thing to this thing via the duplication on the comonoid here. But there should also be a way of going from this to, let's see, let's say actually going from this thing to this thing by deleting one of these D's. And in fact, going like one way and then the other should be the identity because of the comonoid laws, because that's one of the comonoid laws. And we just have a bunch of objects like this, a bunch of morphisms just generated by these sort of comonoid co-units and co-multiplications. Testing? Hello? Okay. I think we're back. If someone could say in the chat what the last thing they heard was, so that I can maybe back up to there. Again, sorry about this, and bear with us as we try to finish this.
Apparently, it had you repeating the word click repeatedly.
Cool. Yeah, so...
I don't have any indication that it's working. I don't have any indication that it's working.
Oh, really?
On the chat.
Huh?
If you look at this, you can see whether this responds to the sound.
Okay. Okay,
Sound
I think
works
people
again.
can hear us.
It is okay
Oh yeah,
now.
there's a lag, so I'm pretty sure the audio is working now.
Okay.
Can I have one of you wear this,
Okay.
and so you can hear what's happening?
Okay.
Yeah.
Hmm?
You want
I
to
think it's
check.
the other ear,
You
but
want to
yeah.
click on this, look at this bar, and see
Yeah.
if it's moving with this voice.
Mm-hmm.
And you should be hearing the
I'm not.
stuff too. You're not?
I'm not hearing
I
you.
think you should put it in the other ear.
Which ear it is?
I think so. It's a yeah.
That's bizarre.
Did
Can
it
you hear?
really matter
Can you
what
hear?
Yeah, I guess I can.
Okay, great. Is the entire thing?
We missed the entire thing from F and delta arrow poly onward.
Okay. Okay. I think that's okay. And considering we don't actually have time left, I will just say this. I will say that, again, the product of C and D is given by the limit of this functor.
It is given functor.
Yes, okay, so this is the monoidal functor from our free monoidal category on two comonoids into Poly that sends each of these comonoids to the two comonoids that we are wanting to take the product of in Poly. So the product of these two categories is actually just the limit of this functor in Poly. And this is a limit in Poly, and so it's going to give us another polynomial. And so it's going to be a pretty natural sort of composition for it, or a co-multiplication for it, and a co-unit for it. Now, instead of sort of going into this, because we don't have, let me just give what the concrete interpretation of this is. And I put concretely in quotes here because I think this interpretation gives you a really concrete I will tell you exactly what the objects are, and I will try to tell you exactly what the morphisms are, although that's going to be a little trickier. Now, basically, the summary of what I was trying to say over here is that this limit is going to have canonical projections into sort of any kind of chain of composites we form with these C's and D's. But it turns out that we're really only going to care about a composite into this sort of arbitrarily long alternating thing starting from C and an arbitrarily long alternating thing starting from D, except actually this isn't quite true either, because we also don't really care whenever these are, whatever goes on the identity, because whatever goes on the identity is kind of fixed by sort of everything else that happens, and so we're really only going to focus on what goes on the non-identity morphisms, like what object of D we assign to the non-identity morphism here. And so the object of this product category, I can write, I'm going to write down the instructions for specifying an object in this category. And the instructions are, we first pick an object, C1, in the category C. Then for each non-identity morphism coming out of C1, so it's going to be, I'm going to call that F1, and I'm going to call its codomain C2. We're going to pick an object D, I'm going to call this D2 in D. And then we're going to repeat this process. So for each non-identity morphism G2 coming out of D2, we're going to pick an object. Pick an object C3 and C, and so on. We're going to sort of repeat this. And then after all of that, we're going to do this again, but switching the roles. Huh?
Sound was gone.
Oh, no. OK.
I mean, it looks okay here, but I don't hear you.
You don't hear me?
I don't hear you. Wait, that just because it was in my ear?
Let me see. Testing. Testing. Hello?
Right.
Sound is still fine. OK. Testing? Yeah. I don't know. These AirPods are maybe, it takes, yeah, I don't know. We'll find some way. Sorry. OK. And then we do this exact same thing again, except switching the roles of C and D. So we pick an object, D1 and D, and then for each non-identity morphism coming out of it, pick an object in C for each non-identity morphism coming out of that, and so on. And that specifies a unique object in the product C of C and D in cat trip. OK. And then what are the, and so the way I think the best way to visualize this is by thinking about sort of these two trees, right? Like if you think of these composites, these are just sort of two giant trees. And you're going to start with an object in C. So you have this object in C and an object in D. And that's going to be the on-object's projections into C and D. So it's going to be some object in C, some object in D. And then for each non-identity morphism coming out of here, we're going to specify maybe an object. Let's just call this one F1, an object in D. For each non-identity morphism coming out of here, we're going to specify an object in C, and so on, and then sort of the same thing over here. And what we end up with are these sort of two trees coming out. OK, what are the morphisms? And let's see. So one way, first of all, you see these as two trees. And the morphisms are going to be these alternating, they are going to be these sort of like lines you can follow out the tree. So it could be, well, first of all, you could either choose the identity, which is just like stay here. That's why we haven't drawn the identities, because that's just like staying in one place. But you can also choose to take a morphism out of C1 here, and then a morphism out of this D2 here, and so on. So it's these, again, these alternating sequences of morphisms out of, from C and D, just like with the free product of monoids. OK, what's your codomain? Well, you might say that we have a problem here, because the codomain, we want it to be sort of whatever tree that's coming out of here, just sort of like our codomains are cofree coproducts. But this is only a tree coming out of C, right? This is almost like 1/2 of an object here, right? Gives us the tree here. We also need a tree coming out of here. That seems tricky, but we actually have a tree coming out of here because this morphism is a morphism from D, so it actually already has a codomain. And so it has some D as its codomain, some object in D as its codomain. And then so, I'm actually going to write it maybe on this other side. And so we just need to build another tree, another one of these alternating trees from here. And the way we build this tree is by looking at, OK, well, we're going to need to start off by sort of every morphism, every non-identity morphism coming out of here. Well, any morphism coming out of here, you can compose it with this G2 to get another morphism coming out of here. And then that's going to have a tree. That's going to have an object of C assigned to it, and then a whole tree there. And then we just put that tree here. The only issue, though, is if it's an identity morphism. If it's an identity morphism, we actually stay here, and then we just give it, let's see, we are going to, let's see, what are we doing? If we have an identity morphism, we're going to stay here, and it's actually just going to be the tree, the same thing, except it's going to be you do the same process, except instead of using G2, you use this F1 here. I realize that's a little bit confusing, but if you sort of draw this out, you can kind of see what's happening. And then connecting these morphisms together are just a way to sort of conjoin these paths together, except you have to be careful when two things either compose to a morphism that's already there, or if they compose to an identity morphism, you have to kind of collapse it down a level and then compose again. And yeah, and you can already see that this is maybe getting a little bit hairy. But we can bring it to something a little more concrete if we come back to our example here. And the way we can think about this now is we can think of this as, right, so yeah, if we take the product of, I'm actually going to draw this like this, just to distinguish these two. If we take the product of these two categories, it's going to be, well, we pick an object from here and an object from here. So let's say we pick both of these two, because that's going to be the most interesting choice. Well, here we have one non-identity morphism coming out of it, one non-identity morphism coming out of it. And now, let's say this was, let me call this C and call this D. So this is from C and this one's from D. Now here we have to pick an object of D. Let's say we still pick this, so it's still going to have a non-identity morphism here. And we're just going to keep going until we eventually pick this, which doesn't have a non-identity morphism out of it. And so we stop. We can do the same thing here. Maybe go a few steps. And we're going to stop there. Let's see. Let me actually make this a little shorter so it's easier for us to draw. And so what does this correspond to in this picture? So this is going to look like something.
That thing is one object.
Yes, and this is a single object. And it's going to look like something that is going to project to both of these black dots up here. But if we follow this morphism, that's actually corresponding to this morphism. So we're going to come down here. But since this is a black dot, we come over here, because that tells us, that's telling us this black dot as opposed to this white dot. But then this tells us a white dot, so that's actually going to bring us over here. OK, but then this also has a morphism coming out this way, given by this one. This is a black dot here, so that's going here instead of down here. There's a morphism here going this way, which gives us a black dot, and then no dot here. Well, this black dot and then no dot is actually the same as this black dot and no dot. This is actually going to come over here to the same one. And that's going to bring us there. Yeah, and so this is the category. This category, if you think about what this is saying, it's saying that this category has n squared many objects, right? Because this could go, you could have like 0 here, or 1, or 2. So some natural number here, some natural number here. That tells us exactly what's happening with these. And then the morphisms, well, if we have if both of these are non-zero, then it's going to give us something over here and something over here. So some pattern over here and some pattern over here with kind of one less arrow to deal with. And so essentially the idea is that each pair like this, assuming these are both non-zero, one of them is going to map to a pair where m is the length of this, n is the length of this. One of this is going to map to something that looks like 0, comma m minus 1. This one's going to map to something that looks like m minus 1, comma 0. And then given, let's see, given one of these things, that's going to map to something that looks like this. Given one of these things, that's going to map to something that looks like this. And then 0, 0 has no maps coming out of this. But then we also have the composites of all of these possible maps. And that's what this category is. And you can see that this captures all of the possible trajectories of what can happen, like what something that has a cofunctor into both these two categories can do. And yeah, I think I'm going to stop there because we've gone over quite a bit. Sorry about the technical issues. Also sorry that this is kind of a particularly confusing concept. And I will admit that we are still like trying to figure out exactly what the best formalism to talk about this is. Because it is, right, like we're trying to capture these in terms of trees. That's maybe, but you have to kind of like identify a lot of these things in the tree together. And so it might not be the most useful way of thinking about it. So I would love to hear sort of other alternative ways to think about this product. But yeah, that's it for today. Thank you. Oh, thank you. Yeah, and feel free to ask any questions. I will be here.